All right, good morning, everybody. Hey, good morning, everybody. How is everyone?
Not too bad.
That's good.
Just trying to get through the last week.
Yeah, sometimes that's the hardest.
Yep.
It's always hard when you can like smell the end of something.
Now all the homework has been put on Canvas, so it's race to get it all done.
Oh, okay.
Other classes,
Yeah,
not
yeah.
as much as
All right, well, go ahead and send me an attendance note. And any questions? All right, well, we were talking about processes yesterday, and we were talking about the fork call. And the basic idea of fork was it was a way to clone a process and create an exact duplicate with one difference. And the one difference is when you make this call to fork, it returns an integer. And the value of that return from the function call will be different in the original process versus the cloned process. In the original process, this will be non-zero. In the newly created cloned process, this will be 0. And that's a way that these two processes, which are now running exactly the same code, can tell who they are. They can look at this return value from the call to fork and identify themselves as being the original, which is the parent, or the new process, which is the child. And so that's great for making an exact copy of ourselves, and sometimes that's useful. For example, if you were trying to do some kind of very expensive computation, you're trying to, calculate prime numbers or something. You may want to make multiple copies of yourselves and have each of those copies work on a different part of the problem, and then in some way try to take the solutions they come up with and put them together. And so you may just want a copy of yourself, um, or you may want to do something slightly different. For example, you're writing a program that lets you edit files, and the user is typing in and they're editing files and so on and so forth, and at some point you want to like automatically save the work, and maybe saving the work is expensive. Maybe it requires making a network connection and waiting for Git to respond and so on, and it's going to take 10 seconds, and you don't want the user who's in the middle of typing something to have to wait 10 seconds while you save their work. And so you might make a call to fork to create a new process and have that new process look at the return, say, hey, I'm the child process, I'm here to save the user's work so far. And that process would go ahead and make a connection to GitLab and send information over and so on and so forth. While in this main process, the user continues to type and edit their files and so on and so forth. And if you make multiple calls to fork, in other words, if this child process made another call to fork, then you would have a duplicate of this process. And this third process, that call to fork would return a 0. This call to fork would return something non-zero. And the non-zero value is the process ID of the new process. So this thread, this process would have the process ID of this thread, and the original process would have the process ID of this first created clone. And so if you use this ps command, so let's do a ps-lf, ps-elf, and so this is looking at everything that's running on my system right now. This is just my laptop, right? And I've got, a bash shell running right here. I've got code blocks for some C++. I've got Clementine, which is my music player, and a Bluetooth daemon, and so on and so forth. Every process, you can see the process ID and the parent's process ID. And right here, I'm seeing a bunch of processes whose parent is 19086. And 19086, that's a process that's just running Clementine. So when I typed Clementine on my keyboard back on November 17th, this process started running, and it created all of these other processes, which are working in support of that original process. When I typed ps-elf just now, that was process 16013. Its parent was 16,000. And if I look at 16,000, that's a process running bin bash. And bin bash, that's my bash shell. That's what we're looking at right now. Its parent is 15,995. That process is called console. Well, that's the name of this window, this program that I'm running. When I hit Control-Alt-T, it opens up this terminal window. That's a program called console. And console's parent is 7896. And if I look for 7896, that's something called xf settings D. And the parent of that process is process ID 1. And there's a whole bunch of processes whose parent is process ID 1. So all these XFWMs, X is the windowing system that most Linux systems use. It's a very old system, predates Windows. And XFWM4, that's the window manager for the X file system, or the XFC system. Here's something, this is related to like monitoring power probably on my system. Here's the power manager, which is, checking the battery charge condition and so on and so forth. These processes are owned by process 1. And if you go all the way to the top and we look at process 1, it's a process called init. And this is the process that is created when your system boots. So it's sort of the first process. And it's the parent of most other processes on the system. So when the system boots up, let's say that I want people to be able to log into my system using SSH. I need to have a program running called SSHD. The D is short for daemon, which basically means this is a server. It's something that other programs can connect to. And if I'm allowing people to SSH into my laptop, I have to be running this program SSHD. Well, when my system boots, the init process, one of the things it will do is look at configuration information and say, hey, do you want to allow people to SSH in? And if I do, it will start an instance of SSHD. How does it do that? It creates a fork of itself, a clone, and the clone will go off and run SSHD, or the XF window manager, or the power daemon, or any of these other things. And so this process is run when the system boots, and it basically creates the other processes on the system. If you do this on the Linux machine, you'll be able to trace back your bash shell to an SSHD instance, which you can trace back to an initial SSHD, which you can trace back to init. And so this mechanism of making clones is instrumental to how basically everything happens, to everything that happens on the system. And yeah, so this is why you can log in more than once, because when you make a connection to the SSH daemon, it makes a clone of itself, and that clone talks to you asks for your password, does the authentication, and so on and so forth, and hangs out while your process is running. But if at the same time somebody else tries to log in, they'll make a connection to the daemon, and it will create another clone of itself to talk to that user. So forking is useful, right? This is a fundamental system call that we need anytime we want to basically do anything. Because every time we do anything in bash, right? If I say what's the current date, well, bash doesn't know what the date command is. Bash won't tell me what the date is. Bash simply looks at this and says, oh, I don't recognize that command. Maybe it's a program. And it looks at a variable called path, and it looks in each of these directories for an executable program named date. And probably when it gets to here under /bin, it finds this thing called date, and it executes this. Well, the way that bash does that is by first cloning itself using fork, and then saying, hey, forget what I'm doing. I don't want to be bash anymore. I want to be /bin/date. And it uses another command called exec to basically change itself from being a copy of bash to being /bin/date. So we can work with all of this stuff, and we'll play with some of this at a low level, but a lot of times we don't really want to deal with forks and execs and all this kind of stuff. All we want to do is just run a command, right? Maybe we just want to clear the screen. And we know that the clear command will do just that. It'll clear the screen. It's a chapter 1 command, and we just say clear, poof, the display gets blanked out. I can't remember what I need to include, so I'm just including a few things here. So I'm going to ask the user to hit enter, and I'm going to let them do that. And then I'm going to do the following. I'm going to say system clear. And then I'll just print out a closing message and I'll exit. Alright, so this is a really useful command. System will basically say execute this command. And when this command executes, this current program will basically get paused while this command starts executing instead, and then when this command finishes, we'll come back and continue executing this current program. So this program should just say hit enter, wait for me to hit something, followed by an enter key, and then it'll execute the system command clear, and that'll print out yay. So if I run this, it says hit enter. As soon as I hit enter, it clears the screen, then my program continues and says yay. So I can throw some sleeps in here. After I hit enter, I'll sleep 2 seconds, clear my screen, sleep another 2 seconds, and then print out a message. So it says hit enter, I hit enter. Oh, but I made a typo. So I'm not calling a function, I'm just executing this sleep command like sleep 2. Alright, so I'll hit enter. It sleeps for 1-2 seconds, clears my screen 1-2 seconds, prints out a message. And we can put pretty much anything we want in here. I could do an ls-l. And it will execute the ls command. So I can say cd to the bin directory and then do an ls from inside there. And now it's showing me the contents of /bin. So let's do a cool test. Let me get rid of this delay in the beginning. Let's just do a test in here. Let's do a ps-lf.
So how are you able to get back into that program so quickly if we change the directory?
Oh, because we changed the directory inside a subshell. So yeah, this is a good point. Whatever runs in here, this is being executed in a separate process. And so in that process, we changed the directory. But when this main program exited, I was in exactly the same directory I started in.
Oh, so you could literally navigate through your whole system, print out that it's just basically one file, and end up still in your same directory.
Exactly,
Just
exactly.
Oh, that's pretty cool.
Yeah. So if we do a PS inside the system, we can see a little better what's going on. This is the bash process that's running, you know, that started when class began. And that's process ID 16,000. That's the parent of this process, main, which started, you know, a minute ago when I said main. And main is 17302. That's the parent of this command, sh-c ps-lf. sh is a different type of shell. Bash is one shell. sh is a different one. It's called the Bourne shell. And so when I said system, my program basically created a new process to execute the following command. sh, which is the Bourne shell, -c, which says don't read standard in. I'm going to tell you a command to execute. And then here's the command I wanted executed, ps-lf. And that process 17303 is the parent of this process 17304, which is executing that command that we asked sh to run for us. So when we say system, a few things happen. A new process is created to execute sh, and sh executes whatever command we put in here, and then that command actually executes because that's what sh does. And if you look at the manual page for system, it'll tell you all this, right? System uses fork to create a child process, and then uses execl, which is like exec, to do the following command, /bin/sh. sh is the program being run, -c is the switch saying I'm going to give you the command, and then whatever command you called system with, that gets executed. And status, you know, the return value from system will be an integer. And sometimes that's useful to look at. So let's execute this command and look at the return value. So So it tells me the return value from system is 0. Which means that my program, probably executed normally. If I have some weird command that doesn't exist, return value from system is 32,512. Means something went wrong. If I try to execute the command ls haha, return value from system is 512.
So 0 indicates that it's run through its process and effectively finished the process, right?
Exactly. 0 basically means no error. So if I try to execute the command ls main, my return status is 0. 0 usually means success. If I list a strange file and I look at $? It's a 2. Well, 512 is 2 times 256. And so we're getting a bunch of information back from the system call. Basically, if it's a 0, you're good. If it's non-zero, there may be something that went wrong. And what can go wrong is that the command can fail to execute, or the system call can itself generate an error. For example, if there's not enough resources to start a new process, then system can itself throw an error regardless of what the command was. All right, so this is good, right? We can say, hey, I want to know what the date is, and we can just say system date, and it'll execute the date command. But if I wanted to use the result of this call to date inside my C program, I can't do it with this. The only thing coming back from system is an integer status. And it's not letting me, take this output that was produced and say, put that in a string and analyze it with scanf or something like that. So if I want to get information back from a process that I'm running like this, system doesn't work. I have to use a different command, which is popen. And so we know how to use fopen to open a file, right? You can say something like file fp equals fopen. Put in the name, put in the mode. And then we could say fgets from fp. If we opened it for reading, we could read from that file. If we opened it for writing, we could do an fprintf into fp and send things into that file. So we can do the same thing to interact with processes instead of files. And the way this looks is it's still a file star, but we say popen. And we have a command and a mode. And mode is generally going to be R for reading or W for writing. If we start a command like this with a mode of read, then any output that this command produces to standard out, we can read that by reading from FP. If we start a command with a mode of W for write, then while this program is running, anytime it wants to read standard in, it will read whatever we've written to FP. So we have our C program, which is doing something. And if we open a process for writing, we create a new thread, and FP basically feeds standard in of this new process. And if we open a process with popen for reading, we create a new process, and FP gives us the contents of whatever this process sends to standard out. So let's do something better with our date command here. So I'm going to run the date command. I'm going to open it with a mode of R, which means I want to read from it. and I'm going to do the following. I'm going to say fgets buffer 120 fp. So buffer should have whatever the date command sends to standard out. And so I'll print out the contents of buffer. I'll delimit it with angle brackets as usual so we can see it. Alright, you ready for this? Oh. So I got an error here, data not found, because I misspelled date more than once. Date. Alright, now we're ready for this. Run our program, and it says the return from the date command is, and there's the output of what date generated. But that output is in my variable now. It's in a character array. I chose to print it out, but you know, I could run it through scanf and you know, do some processing with it, or write it to a file, or do whatever I want. So popen is a pretty painless way to run a command and capture the output of that command. So let's do a different command. Let's execute the command ls. I'll open it for reading. So whatever ls sends to standard out, I should be able to read through fp. So I'll do a loop where I keep reading from fgets, keep reading fp from using fgets until it returns null, which is how I know it hit end of file. And each line that I read from fp, I'll just go ahead and print that out. And now, you know, I can see exactly what my ls command did. I've got 3 files in my directory. If I do an ls-al, alright, now I got 5 lines of output. So this is useful because we can interact with, you know, all of the power that we have by working in a Unix system. We can tap into that from inside our programs. And it takes very little code, right? A popen to start the process, and then an fgets to read, or an fprintf to write. And now every command that I have on the system, BC for doing calculations, ls, you know, df to see how much disk space I have, ifconfig to look at my network status, right? All these commands, we can execute those and look at their output or feed their input from a C program. This is part of why it's nice to have harmony between the operating system and the code that's running on that operating system, instead of just, you know, having a generic C program that runs on whatever, because we can take advantage of the fact that this is Unix. Alright, so that's the input side of the equation. There's a program called BC that I use a lot in class to do calculations. And BC, you know, lets you type something in and it will generate, it'll print out the results of some calculation. Um, all right, so we can play with this. Let's open BC for writing. There's 2 to the whatever. All right, so let's do some calculations. Let's calculate 2 plus 2. So I run main. Hey, give me a 4. So how did I calculate 2 plus 2 without actually doing addition? I opened a pipe to this process BC, which does arithmetic, and I sent it the instruction 2 plus 2. So anybody notice something weird on the output here?
Oh, it never returned.
Well, it did actually. But something weird about the way it returned.
Can you move the console up just a smidge? It's kind of get cut off by the buttons on.
Oh, okay.
Things.
Well, I guess it actually did math when we wouldn't really expect it to. Or I guess maybe that's fprintf, post new printf.
Yeah, so it did the math. We sent this into the BC command, and BC by default outputs to standard out, which was our display. But this was the output of my BC command. This is the prompt I got from bash after my main program exited. My program exited, I came back to bash, and then the BC command finished its calculation. And that might look a little weird, because I'm sending this into BC before I exit. So let's put a print statement out here. Let's just say done when we're done. And now we can clearly see it's saying that it's done before it's actually done. And the reason this is happening is because of something we call buffering. So in computer systems in general, when you try to write to a file, or to your display, or to another process, or you try to do I/O, that's usually a pretty expensive operation. In particular, doing this fprintf means, taking these characters and somehow sending them to this different process. And so, a lot of manipulation has to take place in the operating system to take these 4 characters, 2 plus 2 new line, and feed those into standard in of this process, the process that's running BC. When you write a file to a hard drive and say let's print out the words hello into this file, that's an expensive operation. You have to wait for the hard drive platter to spin if you have a physical spinning hard drive, and move the read write head and send the bits in one at a time and all this stuff, right? So most operating systems buffer I/O operations, meaning when I say print this into my file pointer FP, it doesn't actually print into FP. This print statement actually copies this into memory with a little note saying, hey, when you have a chance, take this thing and send it to FP. And the idea is there's a good chance I'm going to print a bunch of things to FP. And so it's going to wait till I've told it, a whole lot of things I want to print. it's saved all of those up, and then it's going to actually print them all at once. And it's just an efficiency mechanism. But it can make things look really bizarre like this, because it looks like my program exited before my BC command finished. Well, right here I should have asked BC to do 2 plus 2, and instead, you know, my program exited, and then sometime later I got my 4. I can throw a sleep statement in here, and I'll sit here and I'll sleep for 5 seconds, and I've already sent my command to BC. I slept for 5 seconds, then I said done, and then after all of that I actually saw my sum calculated. Well, when I start sleeping, let me do this one more time. Right, I'll print a message saying that I've sent my data. I'll sleep for a while. My data's been sent. How come I don't see the results? And the reason is that even though I said print this to FP, it didn't actually get sent. It's buffered. It's in a holding area. And this will absolutely drive you bonkers sometime late at night when you're trying to debug your code, because I can put a print statement here which says this data has been sent, but it hasn't actually been sent. And the whole essence of debugging with print statements is I can use a print statement to know when certain things have happened. Well, this hasn't actually happened. Well, it actually has happened. The fprintf did execute, but it didn't do what I thought. It didn't take this string and send it into the file fp, which is this process. It put it into a holding area. It buffered it up. And so the magic trick here is we want to flush that buffer. So fflush is a way to override this buffering. And sometimes you can override it just by printing a new line, but if you want to be really sure that what you've written into a file pointer has actually gone through, make a call to fflush. And by adding that one call there, the universe is restored to order. Data has been sent to BC. There's the output of the BC command. We wait 5 seconds. We say done. And everything looks the way it should. So remember this fflush call. It'll save you in future courses. And fflush just flushes a stream. Takes a file pointer, and it takes everything that's been buffered and forces it to get sent out. All right, questions so far? I'm planning to spend Friday and maybe part of tomorrow going over sort of a study guide for the final. And I'll tell you what parts of all of this and other stuff I expect you to know for the exam. I'm not going to ask you to write code that uses this stuff on the exam, but I may ask you conceptual questions or ask you to do some, matching or multiple choice or things like that, related to things like fork and system and popen and the ps command and kill and stuff like that. But we're looking for sort of high level concepts at this point. And you'll definitely dig deeper into these concepts in other courses. Alright, so let's talk about exec. So we know we can fork to create a clone of ourselves. But if we want that clone to do something different, like run the date command, for example, we can't just keep executing a copy of our current C program. And so here, I've got a C program, and my C program is supposed to do all of this stuff. But I want the copy that I make, this new process, to execute the command BC. So forking is part of the process. Forking is a way to create a clone. But once we create a clone, we need that clone to start doing something different. And the way we do that is with exec. So let's play around with this. All right, so exec, there's a bunch of different versions of exec. I'm going to use a version called exec v. Exec v takes two arguments. It takes a name of a command, and it takes an argv, similar to the argv that you have when you execute a main program. Don't worry about this one for now. I just want to think about this. All right, we've got a process. It's running. In this case, the process is called main. It's going to set I equal to 12. It's going to multiply by itself and print that out. So it should say I times I is 144. So it can do whatever we want. It's just a C program, right? But when we get to this statement, something really, really weird is going to happen. When this function is called, the function will open up this file, and it will find the executable code inside that file. The ones and zeros that correspond to the instructions for /bin/ls. And it will basically replace the current process's program memory with those instructions. And then it will start executing from the beginning of those instructions. And all of this, and all of this, and all of this will disappear. Now what happens if you're running one process like this program called GoGo, and partway through you open up a file, you pull out the executable code from there, and you load it into your program memory? What are you doing now? You're running this program. So exec is a way to basically transform yourself into something that's running a totally different program. And because when I make this call, my current program memory is changed with the instructions from this file, I never return from this call. Right? Once I start executing these instructions, the fact that I called this function is totally lost. And I'm definitely never going to execute this instruction, because that was part of the old program memory instructions. And program memory has been replaced with the instructions from this file. So if I run this, it does I times I equals 144. It executes /bin/ls, and that's the end of the program. Right? Why didn't it print this? Because when I made this call to exec, this program disappeared. It was no longer executing these instructions, it was executing the instructions inside here. And that's possibly a really freaky concept. But this is how processes are created and made to do things on Unix. So typically you do two things. First, you make a clone of yourself by calling fork, and then you have that clone change itself into whatever instructions you want it to execute. And if you overwrite the program memory with this, then the program becomes binls. So it's a little Blade Runner-ish, right? You change the memories, you change the essence of the process itself. And so we could do something like this. Alright, we can get rid of the funny stuff in the beginning here too. Alright, so now what is this program going to do? It's going to make a call to fork, and that's going to create two go processes. One of them will see a PID of 0, that's the child process. And so the child's going to print a message saying, I'm changing into bin ls, it's going to exec bin ls. It's not going to do this because after it calls exec, that child process is now running /bin/ls. The parent, on the other hand, is going to say, hey, I'm still the parent, and I'm exiting goodbye. Alright, so first thing happened was the parent said, still here but exiting goodbye, and then the child said it's changing into bin ls, and then ls executed. And partway through the output of ls, our original process go exited, and bash noticed that, and it printed out the prompt. And while it was doing that, this other process was running ls, and we printed out the results of the last line of ls there. And that's going to do something different each time that we do it. This time the parent exited, we got the prompt right up here before ls started executing. So these are two processes with totally independent existences. Alright, so the last part of this I want to go over tomorrow is this business of doing two-way communication with a process. So if we use popen with a W, we can write to standard in of a process. If we do popen with a read, we can read from standard out of the process. If we want to run a new process and be able to both write to it and read from it, we need to do something different, something more powerful than popen. And so I'll touch briefly on some of the mechanics involved in that tomorrow, and that'll probably do us for processes. So we'll spend part of tomorrow doing that, the end of tomorrow starting to review for the final, and then Friday we'll spend just reviewing final questions and so on and so forth. Alright, please send me an attendance note one more time, and I will see everybody next time.